Line up the alkali metals, hydrogen, lithium, sodium, potassium, rubidium, SeZium, pair each one with itself, and measure how far apart the two nuclei sit. In hydrogen it is 0.74 Ang strums, a tight handshake. In SeZium, 4.65, a languid reach, 6 times as long. Orthodox quantum chemistry gets every number in that column right by solving a fresh molecular problem for each pair. This chapter asks something harder. Take one number, read off an isolated atom, never refitted and never touched again. Can that single number set the bond length for the whole column at once? The answer the substrate forces is yes. The answer honesty forces is to about 15%, not to a few. That error bar is not a footnote. It is the result. One thing before we begin, Advaita Chakra Theory is a speculative exploratory framework, not established peer-reviewed physics. Much of what follows is honest conjecture that still needs validation. Watch it in that spirit as ideas to test, argue with, and refute. So here is the discipline that makes that question answerable at all. The chapter is stated on 3 floors, and nothing on one floor may reach the floor below it, except through a single named map. Floor 1 is the substrate, the rotor lattice of the opening chapters, compact phases with integer momenta, coupled by stiffness and pinned by locking. Chemistry needs exactly one export from that floor, the energies of the atomic modes, set by a single Rydberg scale. Floor 2 is the atom. Its spectrum is hydrogen-X in shape, but the nuclear charge is dressed down by the inner shells into an effective charge. Floor 3 is the molecule and the solid coherent combinations of those dressed atomic modes on neighboring cores. Bonding, anti-bonding, bond order, networks. Now the restriction, and it is the whole content of the chapter. That effective charge is fixed entirely inside the atomic sector. Floor 3 refers to floor 2 only through that same effective charge. There is no separate molecular screening law. Put plainly, the substrate hands chemistry exactly 1 dial per shell, and the molecule may not secretly turn a second. I want to be exact about the status of that. It is not a theorem. It is a posited discipline put in by hand, and this series badges that asserted. Its whole value is that it is restrictive. Fix the dial in the atom, and every molecular property becomes a genuine prediction, with nothing left to tune. Whether that restriction survives contact with data is the question the rest of the chapter answers. It does survive structurally, and it strains quantitatively. 2 suspects, and then 2 confessions. Suspect 1: let the molecule refit its own effective charge. That is the obvious road to percent-level accuracy. The theory forbids it, and the refusal is deliberate. Allow a molecular refit, and you have traded a falsifiable structural law for a fit that can absorb any measurement at all. So that suspect is struck off by design, not by evidence. Suspect 2: the clean scaling law itself, taken as a number. Promote the hydrogenic radius to a molecule, and the bond length goes as n squared over the effective charge, with one constant fixed once on hydrogen. That guess captures the ordering and the 6-fold span. Taken as a number, it overpredicts the heavy alkalis by up to 79%. It survives as the skeleton. It is rejected as the number. Now the confessions, and both of them are the author's own. Confession 1: an earlier paper derived bonding directly from the substrate. It recovered covalency, bond order, and the qualitative trends, and it mixed flows. Screening went in as an effective charge with no microscopic map down to the lattice. The substrate to atom boundary was blurred, and the bonding modes were never properly formalized. What you are watching is that paper refereed and rebuilt. The 3-floor discipline and the screening law are the fix. Confession 2. An optimistic reading of this transfer once called it a few percent law. That is retracted. Held against the alkali data, it downrates to roughly 15% RMS scatter, and the headline of this chapter is the downrating itself, not a suppression of it. Build floor 2 properly, then. An outer electron in a given shell carries a hydrogenic energy, the familiar 1 over n squared ladder, with the nuclear charge replaced by an effective charge, and a quantum defect shifting the rungs. Turn it around, the first ion Iy energy is the Rydberg scale times the effective charge squared, over n squared. Measure the ion Washun energy and you have measured the effective charge. None of that is new here. The Rydberg prefactor and the 1 over RKO long tail come from the hydrogen chapter. where that tail is the Green's function of a massless Goldstone mode, and DAG unalizing against it, returns minus 13.6 electron volts times Z squared over N squared. Chemistry inherits that machinery whole and adds one ingredient, the dressing of the bare charge, into the effective one. The dressing is a linear law. Start from the nuclear charge and subtract the inner shells one at a time, each weighted by a screening coefficient, and those coefficients are fixed once and for all from atomic data ionization energies and fine structure. No molecular information enters anywhere. This is Slater's rules, relabeled onto the chakra shell structure standard physics, correctly relabeled. Now run it backwards, invert the ionization relation against the measured alkali energies, and read off the effective charges. Hydrogen, 1.00. Lithium, 1.26. Sodium, 1.84. Potassium, 2.26. Rubidium, 2.77. Cesium, 3.21. Physical monotone, climbing steadily down the column. The implied screening fraction runs from about 0.87 to 0.96. The atomic floor is sound before a single molecule is built. Floor 3. Bring two atoms together and let their outer modes overlap. A normal mode of the effective Hamiltonian is not one atom's mode or the other's. It is a single coherent superposition living on both cores at once. Add the two lobes in phase and the energy goes down. That is the bonding combination, and it is what holds the molecule together. Subtract them and the energy goes up anti-bonding. Count the electrons in each kind, and the difference over 2 is the bond order. The picture underneath is one this series keeps returning to. A bond is two topological Goldstone lobes sharing their overlap, exactly the way a pair of vortices in a SO superfluid shares circulation. The winding that made the electron a unit of charge chapters ago is now the outer shell lobe whose reach sets the bond. The arithmetic is a two-level problem with a closed form. The two modal energies sit symmetrically about the average of the two atomic energies, pushed apart by the square root of the on-site mismatch squared plus the coupling squared. Minimize the total energy against separation, and you have the equilibrium geometry. The curvature at that minimum gives the vibrational frequency. Every line of that is standard physics, the two-level LCAO, Huckel, tight-binding skeleton of molecular orbital theory. The substrate leaves exactly one fingerprint on it. The coupling and the mismatch are not free parameters. They are forced to be functions of the atomic effective charge and of nothing else, which is the restriction from before. Now with teeth the molecule has no dial of its own to turn. Here is where the posit earns its keep. Because the effective charge is pinned in the atomic sector, every molecular quantity is a prediction rather than a fit. For a hydrogenic outer shell, the characteristic radius goes as n squared over the effective charge times an atomic length. One caution that atomic length is not the lattice spacing of the substrate, which lives some 20 orders of magnitude further down. Different floor, different scale, confusing them is a category error. Now the molecule. The bond length of a dimer is dominantly set by how far those two outer lobes reach into each other, so it inherits the same combination, with one constant fixed once on hydrogen. And the ratio of any two bond lengths in the column depends only on the two atoms' quantum numbers and their effective charges. No molecular parameter appears anywhere in it. Now confront it with the column. Plot the measured bond lengths of the 6 alkali dimers against that one atomic combination. They correlate at 0.95 across a sixfold range of size with no molecular refitting anywhere. That is this chapter's genuine content, derived as structure, not as a number. Given the posit, the molecule has no choice but to inherit the atomic dial, and the data say the inheritance is real. Now look at what is not derived. Percent level accuracy. Let the exponent float and the data want about 0.75, not the clean one, and that fit still carries roughly 15% RMS scatter. The naive exponent 1 form, calibrated on hydrogen, overpredicts cesium by 79%. So the honest label is trend level, 15 to 30%, driven by a real link between atom and molecule, and not a few percent law. Put the 3 pieces on the ledger, because this chapter is unusual. It has no dedicated row in the tag audit. The master plan lists it tag neutral, so its tags are assigned from the source text itself. 1. The single screening law posit is asserted, a discipline put in by hand. 2. The screening law, the quantum drift atomic energy, and the two-level bonding split are standard physics, correctly relabeled. Slater from 1930. Rydberg and Ritz, by way of Sactan. LCO and alkali tight binding. 3. The atomic to molecular transfer is derived as structure. What is new as stated is none of those inherited laws. It is the layered discipline plus the finding that the restriction survives the alkali column at correlation 0.95. The ledger entry for the chapter is 4 words. Structural win, quantitative miss. Let us do the arithmetic in public. Anchor on hydrogen, its outer shell has n equal to 1, its effective charge is 1.0, so the atomic variable n squared over the effective charge comes out at exactly 1. The measured bond length of the hydrogen molecule is 0.741 angstroms. Calibrating on that 1 point fixes the constant at 0.741 angstroms. That is the whole calibration. 1 measurement, 1 number, and it is never touched again. Now predict cesium, which we have not used. Cesium's outer shell has n equal to 6, and we read its effective charge off the ionization energy 3.21. So its atomic variable is 36 over 3.21, 11.21. 2 laws, 1 prediction each. The naive law, exponent 1 multiplies straight through 0.741 times 11 of 21 gives 8.31 angstroms. The fitted law, exponent 0.75 raises the variable to that power. First, 11.21 to the 3/4 is 6.13, giving 4.54 angstroms. And the measurement, 4.65. So the naive law lands 79% high. The fitted law lands within about 2%. That single comparison is the whole chapter in miniature. The ordering and the scale come free from the atomic dial. The naive law already knows cesium's bond is roughly an order of magnitude longer than hydrogen's without ever seeing a cesium molecule. But the exponent that turns a trend into a number is an empirical 0.75, not the clean one. 2 more predictions ride on the same dial, and both can be checked. First, scale each bond length by its own atomic radius, and the dissociation energy, measured in units of that atom's ionization energy, should collapse onto one master curve, fixed once in the hydrogen sector. Empirically, the heavy alkalis, sodium through cesium, cluster tightly at 0.12, within 8%. Hydrogen and lithium sit above the band, and the chapter states that rather than smoothing it away. Second, the vibrational frequencies have to soften monotonically down the column, because the bonds are getting longer and slacker. They do. 4,401 per centimeter in the hydrogen molecule, down to 42 in cesium's. 2 orders of magnitude in the right direction, with no new parameter anywhere. So what would break this? The construction was pre-registered as a 6-point scorecard against real alkali column data, and the companion code reproduces it number for number. 1. The effective charges come out physical and increasing 1.00 up to 3.21. 2. The implied Slater screening lands between 0.87 and 0.96. 3. The bond lengths correlate with the atomic combination at 0.95. 4. The heavy alkali dissociation ratio holds at 0.2, within 8%. 5. The vibrational trend is monotone, 4,401 down to 42. And 6. The one most theories would leave off their own scorecard, records that the law is not few percent. Naive off by 79. The fit at roughly 15% RMS. Here is the kill test, and it follows directly from the restriction. The transfer forbids a molecular refit, so take a second column of the periodic table or nuclear dimers, 2 different atoms bonded together. If reaching even trend level accuracy on those requires an effective charge different from the atomic value, the deposit is falsified, not weakened, falsified. The sharpest single target is the master curve because it is the least forgiving thing in the chapter. Every alkali dimer must lie on one curve fixed by hydrogen alone. Any dimer that sits off it is a counterexample. All of it is checked by machine as well as by hand. The routine inverts the ionization energies to the effective charges, builds the bond lengths with the hydrogen calibration, and reports the correlation, the band, the softening, and the error accounting. Fixed inputs and not one molecular fit parameter. 3 things are honestly open, and the first is the exponent. The data want 0.75. The clean scaling says 1. That gap is not noise. It is missing physics, and the chapter names it. The coupling between the 2 lobes depends on how far apart they are. So does the repulsion between the 2 cores. Neither of those is computed from the substrate here. Both were absorbed into a fitted exponent instead. So the single object that would close it is unusually specific, a substrate level derivation of that overlap coupling, as a function of separation and of the screened lobe shape, which predicts the exponent and predicts how it drifts from one column of the table to the next rather than fitting it. Get that? And the trend becomes a number honestly. Until somebody does, it is fitted. Open thing 2, the master curve. The function those dissociation energies collapse onto is measured, not derived. A first principles version of it would turn the collapse from a well-behaved fit into a genuine dissociation energy prediction, and nobody in the corpus has one. Open thing 3 is the narrowness of the test. 1 HOMO nuclear column, 6 molecules. Heteronuclear dimers are untested, and so are the extended networks of floor 3 solids, bands the condensed matter end of the ladder, which is exactly where a one-dial restriction is most likely to strain. None of that touches the foundations of the substrate. They are the ordinary frontier of turning a structural law into a quantitative one, and the debt is carried openly to the honesty ledger in part 7, where mechanism and precision are scored separately on purpose. The verdict in 3 sentences. 1. A single effective charge fixed inside the atom from ionization energies alone and never refitted controls the bond lengths of an entire column of molecules. It correlates at 0.95 across a 6-fold range of size. 2. That transfer is derived as structure, not as a number. The number it delivers is trend level 15 to 30%, because the exponent the data want is 0.75 and nobody has derived that yet. 3. The restriction that makes the whole thing a prediction rather than a fit, 1 dial per shell, and the molecule may not turn a second, is asserted, put in by hand, and it carries its own kill test in the heteronuclear dimers. The motif holds in the smallest possible way. 1 substrate, 1 gold stone, 1 effective map, and here that map has a name and a rule. The molecule may not invent a second one. A chemical bond, on this picture, is 2 topological lobes sharing their overlap, the way 2 vortices in a superfluid share circulation. Next chapter, the same channel symmetry logic that keeps chemistry to 1 dial, applied 1 level up, where it selects the gauge group itself. Until then, here is one to try. It needs nothing but paper. Take potassium. Its effective charge is 2.26, and its nuclear charge is 19. Work out the screening fraction, nuclear charge minus effective charge, over nuclear charge minus 1, and see for yourself how close to 1 it comes. A word of acknowledgement. This work was inspired in part by the non-dual teachings of Sri Narayana Guru, that the creator, the creation, and the substance of creation are fundamentally one. Symbols from the Hindu tradition, the Sudarshan chakra and the Shiva linga, suggested the analogies behind the chakra model. They are acknowledged as philosophical and symbolic inspiration. The physics stands on its own. Thank you for watching. If this made you think, please like the video and subscribe. It genuinely helps this work reach the people who will argue with it properly. And do leave a comment, tell me where you think I am wrong. Every chapter in this series names its own kill tests, and the objections are the point. The book and the next chapter are linked below. Until then, 1 substance and how far it reaches.